Welcome to Real Physics and my opening talk of the wonderful conference Demysticon 2025 in a marvelous place, Sesimbra, Portugal, the oceanfront resort. Fantastic organization by Sheila and Anastasia running the Demystify Sci podcast. You should subscribe. Well, my title was The Challenge of Doing Fundamental Physics, and it was a challenge to give it. Listen yourself.
Welcome to our very first session. We have a couple of talks this evening before we go to dinner. Dinner will be at 7 o'clock in the restaurant that is actually on this floor, so it's very convenient. But before that, we have to dive into the realm of ideas and set the theme for the weekend. And so to do that for us, we have Alexander Unziker of Unziker's Real Physics, who was really an extraordinary character to find. So, as many of you probably know, many of the people who we have on the podcast come directly as recommendations from people who listen to the podcast. And so that's either through Discord or through the Sunday chat that we have. And over again, people were like, you guys have to talk to Alexander Unziker. And I'd go and I'd look at his website and his videos, and I'm like, there's this German guy who's in the woods talking about physics, and he's got these like really kind of kitschy thumbnails, and I was like, who is this guy? And then we met Alexander for the very first time, and I immediately felt like we had found someone who, I hate to say this, which sounds very communist, I don't mean it in the communist way, but he was a fellow traveler. It was somebody who understood what we were after, someone who was looking at the world in a way that felt very resonant with the way that we do. And so I'm very, very excited to hear Alexander present on the challenge of doing fundamental physics as an entrance into this long weekend of discussing just how difficult it is to understand nature. Please.
Thanks a lot for this very nice introduction. The challenge of doing fundamental physics is my talk, and I guess the first challenge will be to do this in 30 minutes or 60 minutes, so don't be mad with me if I go a little bit beyond the 30. I will have time for your questions and you will meet me. I also skipped the speed dating. Apologies for this. I'm really honored to give this opening speech here. And when you're doing a keynote speech, you're supposed to be kind to everyone. So let me embrace you with a few cruelties and provocations. Why we are holding physics conferences to begin with? Well, because physics is important. We are discussing fundamental aspects of nature, and we need to meet in person, and we have these creative encounters, and well, that happened. The most famous physics conferences maybe in Solvay, 1927, and now we're going to repeat that. Right? Careful. I mean, consider that. Back then, the top-notch physicists gathered every 3 years. Right now, we have dozens of physics conferences spread all over the world with thousands of participants. We are just a handful of guys pretending to be something special. Times have changed. Okay? I put the Solvay conference because Solvay represented the top, the climax of theoretical physics. Now, I hate to say it, I believe we are in dark ages, literally. We have something like 50,000 publications about things like supersymmetry. ChatGPT counts such as 10,000 to 15,000 astrophysicists, among them several thousand cosmologists, and their output is parameter fitting. So I think that billions and billions are squandered for trivialities in today's science, while the deep important questions lay unanswered on the table for a century. that really requires a department of scientific efficiency. And thanks very much for organizing this event. It's really a great thing. And at least a dose of healthy skepticism. That's what we need. Well, let's have a look at the history of science. There's a very good book from Derek de Soya Price, and he recounts that he had read line by line the philosophical transactions of the Royal Society of London, published from 1662 to 1930. You know, one person could have the entire knowledge of physics at the time 100 years ago. And what we have today, I mean, you can spend all your life reading every second page of Physical Review. You don't even get smarter, okay? So we have this exponential growth of publication, and we don't need a pandemic to understand that exponential growth is something unhealthy. So just to show you that how much times have changed, and yeah, a few scary numbers also. Estimates about, I have to read this, yeah, papers published on SUSY, on something on that. I think science is in a period of degradation, and probably many of you know the joke of Max Planck, science advances funeral by funeral. I think he's wrong. I mean, that was correct 100 years ago when the old skeptics died out who wouldn't like quantum mechanics and all the modern physics, that all the breakthroughs we had at the beginning of the 20th century. So I think it's the opposite with every funding, with every new projects. This kind of degeneration only increases. And I totally agree here with Sabine Hossenfelder. She says, interestingly, it's not a crisis, it's really a degeneration, because science is something you have hope that something will change soon and improve. And I'm not sure. I really would call it as well. And I have some ideas about the true reason, because I agree with most of the things Sabine says, but sometimes she misses the why. So I have a theory what's the reason behind it. And there are some cultural reasons. This book is so scandalous that it's the only one Sheila and Anastasia were afraid to discuss it on their podcast. So, but this is a sideline. I wanted to express some hope, or not, if you like. I think science and academia in its current form will collapse. At least it's unstable, and the instability can last for a long time. But I think the emergence of AI now will accelerate this process, or at least, well, create something very big. The way science is done, it will change dramatically. I know this is a sideline, but I think it's a sideline too important not to be mentioned here. And by the way, I can't wait that these 50,000 publications about symmetry, that ChatGPT learns all this nonsense and creates new papers day by day, and yeah. So artificial intelligence could easily generate 1,000 string papers, you know? And I mean, this is, how to say, reductio ad absurdum. You can't go ahead this way. So I think we have to expect such a collapse of science. And well, let's go ahead. Let's start demolishing the lambda CDM model. And we're all in agreement, right? Yeah, yes and no. I mean, I certainly will enjoy when Eric afterwards will shred to pieces the standard cosmology. Will you do, Eric? Yeah? I'm sure he will do. Yet, I'm also afraid the day after tomorrow, Eric and I will disagree about the alternative. So this is the problem, and we should also be aware of this. We are individuals, okay? I'd agree with you, but then we would both be wrong. And yeah, we are independent thinkers, and this is sometimes unpleasant. And I think as a reviewer on Amazon, on trashing one of my books, he phrased it like that: Unzicker is not the kind of person you want to have in a committee, okay? So we should expect that we disagree, and this is necessary. It's necessary that we support this disagreement, and I call this the problem of sailing between the Greek beasts Scylla and Charybdis. One thing is waste your entire professional life by building on wrong concepts. That's what maybe most physicists, in my opinion, do. Or squander your time in vain by doubting the obvious. I mean, I also risk in doubting very much. I want to see this with my own eyes. I want to do the experiment myself. You can't do that, okay? If you're doubting everything, if you're not relying on the groupthink, so to speak, you're also in risk. And it's a very, very tiny line to walk, and a dangerous line. I addressed that once in a video. I believe in evidence, but where to draw the line? Do you believe in neutrinos? Do you believe in quarks? Do you believe in dark matter? Do you believe in the Big Bang? Do you believe in the redshift? Do you believe in Newton's law? Do you believe in electromagnetic waves? Okay, yeah. Where to draw the line? And so we should not be afraid of disagreement here, but on the other hand, you need to be an independent thinker. And once you are an independent thinker, you have these difficulties. I wanted to play a clip from the Nobel laureate Geoffrey Hinton, but it doesn't play out, but I know it by heart. And he said, you have to be a contrarian. You have to be convinced that everyone else on Earth does things wrong, and you're the only one who's doing things right.
You have to be contrarian, yeah. You have to have a deep belief that everybody else could be doing things wrong and you could figure out how to do them right.
A little bit of this is needed if we are independent thinkers. We should have the courage to do that. And, well, Geoffrey Hinton is one guy. Another Nobel laureate of literature. Every true man must learn to be alone in the midst of others and, if necessary, against all others. Roland, a Nobel of literature. And, well, let's get to physics. Maybe you can say it's telling that I quote all these guys, because the physics discoveries haven't received so many Nobels, maybe, yeah. In the recent times, people were complaining that Geoffrey Hinton had got the Nobel for physics, but it wasn't physics. So, but you can think then deeper in that. Why is that? There are so few real discoveries that merit possibly a Nobel Prize. Few are calmly to pronounce opinions that dissent from the prejudice of their environment. Most are even incapable ever to reach such opinions. I really like that quote. You want to have some more reassurances, right? I bet you want. I bet you want. Karl Popper, the intellectuals make ideologies out of their theories. Unfortunately, also in physics, many ideologies exist. Who does not follow the fashion easily drops out of the community members which are taken seriously. And Louis-Victor de Broglie, the founding father of quantum mechanics, if one had taken the ideas of these scientific geniuses who have been the promoters of modern science and submitted them to committees of specialists, there's no doubt that the latter would have viewed them as extravagant and would have discarded them for the very reason of their originality and profundity. And one very last, in the sciences, the authority of thousands is not worth as much as one tiny spark of reason in an individual. So, what are we going to do? Everyone has heard these reassurances. What will happen after the concerts or in this conference? Will we, a collection of creative minds, join our forces, overthrow the existing paradigm and kickstart the damn needed scientific revolution?
Yes.
I'm the skeptic. Or will one of you, one of the smart individuals participating, eventually convince the rest of us of his theory, new physical theory, that will conquer the world? I mean, Columbus started right next door here. It would be the right place at least. Well, careful. And if I write own perception, I know what I'm talking about. You know, each of these guys has been demonstrably wrong about a very fundamental aspect of reality, of nature. How could we, of all people, pretend not to be? So I liked very much what Anastasia recently said in one of your videos. Ideas that might not be correct, but might lead to inspire something.
Shiloh actually made me say that.
Anyway, it was a co-production, but I really like that. Yeah. So, how are we doing science in all this mess? Let's recall a few serious principles of good science. And Mike Disney is a famous astronomer, and that's why I'm saying. I mean, it's not that Planck. He's one of the older generation. The smart guys are dying out, and he's not died for good thing, but he's now 85. So the currently fashionable concordance model of cosmology has 17 independent free parameters. 13 of these parameters are well matched to the observational data, while the other 4 remain as buffers. This situation is anything but healthy. So just let's recall that basics of epistemology and methodology of science, And of course, this is nothing new. I mean, Thomas Kuhn has written a book, The Structure of Scientific Revolutions, about normal science, about paradigm shifts, about the complication. I think that's what we can observe in cosmology, the increase of free parameters, the excuses that are invented when you come up with a discrepant observation, and so on and so forth. And, well, also Kuhn was not new. If the Lord Almighty had asked me before imparting creation, I should have recommended something simpler. That is King Alfonso of Castilla, and he said that in Portuguese. I know that. Se o Senhor Todopoderoso me tivesse pedido antes de embarcar na creação, ele deveria ter recomendado algo mais simple. That's to be reminded. Yeah? When he visited the library of Toledo with all the epicycle astronomy, he came up with that. He was not a scientist, but has just a healthy intuition, so come up with this. Yeah, well, and of course, in the same direction, we have Occam's razor, simplicity. You should prefer a more simple theory than a complicated one. I would like to generalize this. Look for simplicity in natural laws, because anything arbitrary needs to be explained sooner or later. We are physicists, we want to explain. Yeah. Well, and Occam fought the Pope and died in Munich, so if I'm lucky, I have more than one thing in common with him. So, and of course we have Karl Popper, falsifiable. Is inflation falsifiable? I'm not talking about strings this time, but is inflation falsifiable? How falsifiable has the standard model become? That are legitimate questions. But today I want to focus on, well, a kind of combined concept of Popper and maybe Occam, or also Schopenhauer comes in here. The question of why is the fundamental form of all science. Let's ask the questions. Let's ask, why is it that? even if it's something which seems well established and nobody wonders about it any longer, but yeah, you just should question everything. And what we start from the most important discoveries in science. Yeah? I think this was the most consequential discovery of humankind that changed our civilization forever. You know, the insight, the basic insight. Wow, light is an electromagnetic wave. Okay, and of course you needed a couple of smart people, Kirchhoff, Weber, Maxwell, and Hertz, who eventually verified this with his experiment. And at the very end, this boils down, however, to one equation. Mu naught, epsilon naught, the electromagnetic constants are equal to 1 over c squared, the speed of light. So you kind of explain the way a constant of nature. You had 3 constants before, and you have, by using that equation, only 2 constants left. And that's the essence of progress. Yeah. By the way, I should emphasize here, look out for these coincidences, okay? Back then in 1856, I think Andreas knows it better, he explained to me one time. You tell the audience afterwards what's the correct version, yeah. But more or less at this time, Kirchhoff and Weber had this spectacular insight, wow, that could be the speed of light, okay? So be aware of these so-called coincidences. And I took this example to make, well, a theory of science as theory of science development. And it's now in minute 30, I think, of my talk where the first original idea comes. I tried to set an abstract frame to this. Scientific revolutions are characterized by a visionary idea. Wow, it could be an electromagnetic wave. Of course, then you need this tedious mathematical formalism, which is Maxwell's equations, or even other equations of electrodynamics. But at the very end, you have an elimination of a constant of nature. This is an article where I talked about this. You can look this up in Physics Essays. And this 2/3 in my book, The Mathematical Reality, are about this, at least I discussed this under this aspect of the 3 points. Visionary idea, mathematical formalism, and elimination of constants of nature. So, of course, such a visionary idea can have certain stages and may last for 2,000 years. For example, the Greek philosophers Leucippus and Democritus, they had the idea of all matter being built of atoms, and then we had eventually, at the beginning of the 20th century, the complete explanation, let's say, of the periodic table. And, by the way, the man who completed this revolution that was an amateur, yeah? Antonius van den Broek, who was a lawyer, and he was the first one to come up with the idea that chemistry is determined by nuclear charge, by the number of protons. And of course, I forgot a lot of other people. There was Dalton in between, and Mendeleev and Maya, and many others. It's not in a strict sense that this visionary idea has to be of one person or at one moment. There are many stages. So we had already the second example, Newton's law of gravitation. Well, what's the visionary idea? Mundane and celestial gravity have the same origin. Wow. I mean, it sounds banal nowadays, but in 60, 80, I think this required an incredible imagination and incredible courage to state that. And, not only, there's also Hooke to mention here, but of course Newton had to work out mathematically his theory. It's not just the inverse square law, it's also he thought 10 years about the potential, how to do the integrals, very difficult. But at the very end, we have an elimination of fundamental constants. Because Gm over r squared is local gravity here. Yeah. switching back to electrodynamics for a moment. Everyone sees that it has changed our civilization. But otherwise, if we had this formula, we would have 90,000 constants of nature in the solar system, with each body having this surface acceleration, this local gravity. And this would be considered constants of nature for Martin, maybe, okay, who measures there the local acceleration. So scientific progress is explaining these numbers, explaining these messages of nature, explaining the 9.81 by others, and possibly simplify things. This is a huge simplification. And you may apply this also to other fields of science. One example is thermodynamics. Robert Meyer in 1842 was like, wow, sailing in the, I don't know which ocean it was, but he had the insight, oh, temperature is kinetic energy. The energy of the waves have somehow to transfer into another form of energy. And of course you have the theory needed is kinetic gas theory, but at the very end you have the elimination of a constant. Some of you may say, no, you're mistaken. K is not a constant. K is just a definition of temperature. Yes, it is. But in defining temperature that way, you already had understood the insight of Joule and Meyer. No? This is progress, simplifying things. Johann Jakob Balmer observed in 1885 the spectra of hydrogen atoms, and sometimes the second step, the mathematical formalism, has also to be anticipated. What he discovered actually were shells, but he found this wonderful formula, and it was an enormous simplification. Because, let's clarify here what I mean by constant of nature. I mean it in a more general sense, that every message of nature, every mass, every spectral line, everything what you can measure is a constant of nature. And then you find a law and you simplify it, and these boil down to very few numbers. But this is an incredible insight, that all these spectral lines, and not only hydrogen, but hundreds and hundreds of lines, are buried in this Rydberg constant and the fractions of natural numbers. That was actually the beginning of atomic physics. And then, quantum mechanics. Tell me what's the essence of the revolution of quantum mechanics. At the very end, it boils down to an explanation of Rydberg's constant, found 30 years earlier by Balmer, and you express it by other constants of nature, the electron mass, the charge, and so on and so forth. This is an incredible insight, an incredible simplification. And of course, you need theories, the quantum mechanics, the Schrödinger equation, but I should say the spectacular visionary idea was indeed H, Planck's constant, acts as an angular momentum of the electron surrounding the nucleus is an angular momentum of the atom. That's the visionary idea. And it's so simple. We may not notice it nowadays, but it took an incredible intuition to find that out in 1913. Now let's come to things which are not completed, and quantum electrodynamics doesn't exist. I'm quoting Dirac later, but that's one simple reason why this is not a complete thing. Because if it were a complete theory, you would have to calculate the 137. And also Feynman said that's a damn mystery of physics, you have to compute that. We can measure this number, but we haven't calculated it with a computer without putting it in secretly. So I admit that there is some nice idea, light versus virtual electron-positron pairs, that certainly reflects something deep in nature, but all the stuff of renormalization and is not complete, to put it mildly. And I have a video here it's also in one of my videos on my channel. It's like that. Mr. Dirac, two young physicists approaching Dirac. We have a new theory, listen to us for a minute. And I said, can you calculate the fine structure constant? No? And come back when you have done it. So, well, my message here is that we should focus on this important, deep questions, not lose sight of them. And, okay, of course, 1836 is another number. Dirac pondered for 10 years the proton-electron mass ratio. It's a very deep riddle. And another number, even more scary number, is, that eventually relates to cosmology again, sorry, is Dirac's large number hypothesis. The ratio of the electric and the gravitational force in the hydrogen atom is 10 to the 39. And it's very similar to the extension of the universe with respect to the radius of the proton. And there is even a nicer way to phrase it. I come back in my second talk. But that's not the only thing. I mean, one thing you could call a coincidence, but if a spectacular second coincidence hits the same target, you know, I mean, you divide the mass of the universe by the mass of the proton and you come out with the square of that number, that's not just coincidence anymore, okay? Yeah. People are calling this numerology. It's just numerology. It doesn't go into my head, you know? Kirchhoff and Weber were also doing numerology. Damn. I mean, pay attention to these messages of nature and think about it. It's your job as a physicist to do that. Now the quotes. Well, that's essentially, there are no constants of nature, says Einstein's. Arbitrarily chosen by God do not exist, and that their alleged existence. No, sorry, I'm reading the wrong quote. Yeah, it basically says there are no constants of nature. This is maybe more catchy. Numbers arbitrarily chosen by God do not exist, and their alleged existence relies on our incomplete understanding. I cannot imagine an arbitrary number which could have been chosen by the Creator in just another way. So this is my credo. I think we need to wonder about constants of nature. Constants of nature is the royal road to fundamental physics. It's our job as theoretical physicists to strive for explaining, to look for theories with explanatory power, not only creating new parameters and fixing things. And, well, I call, if someone wants to believe that the gravitational constant is just a God-given number, I say, okay, these are the gods of modernity. God wrote the number 6.673 times 10 to the minus 11. Give me a break, okay? It's impossible. You have to, it's your job to explain that. And if some of you at the end of the conference comes to me and said, Mr. Unziger, I have a new theory of cosmology, my answer will be, can you calculate the gravitational constant? No. Come back when you have done it. So I think this is a very essential problem. And there's a nice anecdote about Heisenberg and Dirac, and they're making up theories how to build physical theories, comparing it with climbing mountains. And Dirac's saying that you have to do that step by step and one step after another, and then you have to reach something, you can look out and what's the best path. And Heisenberg said, no, you have to look first at the entire mountain and then sort out the details later. I side with Heisenberg in this general aspect of how building physical theories, but on the other hand, I have much more sympathy for Dirac and his ideas, because Dirac was the really intuitive physicist who linked in his bold large number hypothesis atomic physics to cosmology, and that's, I think, we have to follow. And Heisenberg was too ambitious. The guy was too ambitious and said, at the Solvay conference, the majority of people were thinking that the Copenhagen interpretation is right, so I have won. No, science is not done by majority decisions. So, to conclude, cosmologists are often in error but never in doubt. I would argue, kosmologi često ошибаются, но никогда не сомневаются. Nobel laureate Lev Landau. And let's not do cosmology in this way. Let's ask the questions. And I should say also let's do that, however, in a respectful way. It's not that we should communicate the way how crazy you need to be to believe in this, to work on this shit of the standard model, or how cranky you have to be not to understand what is established for a decade. Okay, just talk naturally and ask questions. And I think there are a lot of open questions. I listed the first 3 questions. I think they're a little bit superficial. Why there is dark energy? Okay, you can make up theories about dark energy, but maybe we have to go deeper. Why there are discrepant age measurements of the Hubble constants? Okay, but there might be something deeper hidden. Why there is so much structure today? It's a huge problem. I think also Eric will address that. I mean, nothing more or less fits if you just put the cosmic evolution into a computer. It's, you have to pull out the dark matter to get that right, and that's not satisfactory. So I think the more profound question is, why does G have the value it has? And I will come with a hypothesis then in my talk the day after tomorrow. Why there is a cosmological redshift at all? I think that's worth pondering, and that's, I mean, I don't see anybody discussing this, and it's such an important question. We need explanatory power. Why there are these cosmic coincidences noted by Dirac, and how are gravity and inertia related? It's one particular topic I'm in right now, because I kind of rediscovered the 1953 paper by Demysticon, but I will talk about this on Saturday. Let's try to ask questions. Let's listen instead of teaching, which is particularly hard for me since I earn money by teaching. But let's listen. And let's not try to give answers in the first place, but to ask questions, because this is the essence of cosmology. Where the hell did it all come from? The ancients and the moderns. Thank you very much.
In light of the time, Alexander's going to give another talk later this week.
Well, I hurried up for you, yeah?
I want to make sure people have a chance to...
So we need about 10 minutes to turn everything around, and so we only have 5 minutes, which I think would probably be only enough for one question. So is there someone who has a burning question that they would like to ask?
By the way, if you ask questions this weekend on the mic, you will end up online, so be aware.
So yes, burning question plus okay with being on the internet.
So does anybody have a question for Alexander this time?
Anyone?
I have a quick comment about the Solvay.
Please come up to the microphone.
I would just like to point out that on the Scylla and Charybdis slide, many people are both. So
yeah, you can fall
it is possible
both
to die both ways at the same time, for example, if you're a young Earth creationist.
Okay. That's not what we strive for. Yeah.
Very general question. Do you think let's say, how to calculate G from more fundamental parameters is more important than any other question here? Or can you find a question which is even more important? So for example, you also talked about the proton mass, electron mass ratio.
Okay, this is obvious, important proton electron mass ratio you can, but it's a matter of taste. This is a 1836. I like it better than calculating 137. I don't know. I mean, it's a matter of personal choice, which probably you want to dedicate your work to. I just think that the gravitational constants calculating is the least obvious in modern science. It's swept under the rug, the problem, and of course it's rephrased in the most crazy way that you say, oh, the universe is closed and we need inflation, but if you have the gravitational constants calculated, your universe is closed by definition, so you don't have to worry anymore about it. You don't have to worry about that. So I think it's really, yeah, it's the essential question of cosmology, and there have been bright minds investigating this, Demysticon in the first place, but as I said, it's my personal fancy certainly, but I think it's one of these very profound, important questions we need to solve, but it's also just maybe the first one in a row. And I see a little bit more possibility to get to something here, to get something done, because I have no idea how to calculate 1836. Sorry. Yeah.
Yeah, just also like to advertise the posters. There are two people here who present the poster trying to explain this proton-electron mass ratio.
I'm free to see that, but remember, we are disagreeable people.
While we're on the topic of posters, everybody should bring their posters to the morning session, or we'll put them up right after the morning session is over too. We'll be hanging them around the room.
If anybody wants to help us coordinate that, we would appreciate helping people and volunteers. But for right now, I would say let's take 10 minutes and then we'll have an area corner. And so grab a drink. I think everything's still out on the balcony. If you want wine or fizzy water, water's over here. The restroom is down the hall. And let's give Alexander one more round of applause. Thank you for that.